Jai Hind everyone, myself Sandeep Yadav, Assistant Professor CSC Department in Ajay Kumar Garg Engineering College. I am teaching DBMS in the current semester, and today we will be discussing the various concepts relating to normalization that is the part of unit number 3rd being taught in AKTU University for BTech, CS, CSC, IT and all other computer science related branches. Well, we will be discussing the following topic in today's lecture: functional dependency, its definitions and type of functional dependencies. Thereafter, we shall be learning inference rules. Then we will be learning closure of FD set, closure of attribute sets. So, first of all, before proceeding further, we must know what is normalization. Normalization is a technique to reduce the redundancy in the data. See, redundancy is a greater evil in database. Despite the several attempts to remove it, we have been not able to remove it so far. So, we have to remove that redundancy, and that redundancy is being removed through the process of normalization. So, what happens in normalization is that a larger and complex relation having redundancy and various types of anomalies such as insertion anomaly, deletion is being decomposed into smaller and relations. So, in order to achieve that, first of all, we should know what are the FDs, which type of FDs we need to be removing in order to accomplish the motive of normalizations. So, first we shall be studying functional dependency and its type. So, let us learn one by one. First, we will be discussing what is functional dependency. Let us consider a definition. Let R be a relation having n attributes A1, A2 up to An, and this is a relation, student relation having attributes so having the attribute roll number, name, marks and grades. This relation is having the 4 attributes. So, some of the attributes are dependent on other attributes for their existence. So, these are the dependents. Let us consider 2 attributes and x, y, which are the 2 subsets of the relation R. Now, if the values of x component of a tuple determine the value of y tuple, then we say that there is a functional dependency that exists from x to y. This is denoted as this way, where x determines y, where x is known as determinant and y is known as dependent. For example, consider our following relations where we can see that marks are determining grade. A student having 91 marks is getting A1 grade, a student having 73 is getting B1 grade and 87 is getting A2 grade. So, in real time example, we are already seeing that marks determine grades. So, that is also an example of functional dependency. One thing more, this x can be a single attribute or it can be a combination of attributes. We can also say it is y is functionally dependent on x or x functionally determines y. Now, let us see the diagrammatic representation of functional dependency. This is how, if there is a single attribute, then this is the diagrammatic representation which says that this x is determining y. Now, in next example, x1 and x2 are determining y. So, here we will list all the attributes in the box. Thereafter, the edge will be from the determinant to the dependent, that is both x1 and x2 combinedly there is a edge from there towards y. That shows the composite attributes are determining y. Next, here x is determining 2 attribute y1 and y2. So, this is how we will be representing, that is, there is one edge from x to y1 and another to y2. That is how we can represent when x is determining multiple attributes. Now let us consider an example where there is a relation account having the attribute account number, balance and branch. Account number can determine balance and branch. So there is an FT from account number to balance and branch. So this is how we can write it. Account number determine balance and branch. This is an FD that we can show. Now diagrammatically representation is in this way. Account number is determining balance as well as the branch. This is how we can represent it diagrammatically. Now various types of FDs. First is full functional dependency, that is, in a relation the attribute B is functionally dependent on A if B is functionally dependent on A but not on any proper subset of A. That is, if A is determining B, then the subset of A should not determining B. That is, it should be completely dependent on A. Its components of A will not be determining B. That is, let us see an example where roll number, semester and department is determining SPI. Then we need all these three attributes to determine SPI. Next is partial functional dependency. Here the attribute B is partially functionally dependent on A if B is functionally dependent on A as well as any proper subset of A. That is, if there is some attribute that can be removed from A and still the dependency holds, then it is partially functional dependency. Let us see the example. Enrollment and department name determine the SPI. Now enrollment number is sufficient to determine SPI. Department name is not required. So the subset enrollment is also determining SPI. Therefore, it is an example of partial functional dependency. In partial functional dependency, the subset of A also determines the attributes. So that is an example of partial functional dependency. Next is transitive dependency. Suppose A determines B and B determines C, then we can say that A determines C. That is, C is transitively dependent on A via B. Let us see a relation having three attributes: subject, age and the faculty. Subject lists are DBMS, DS and DF. The faculty name is Shah, Patel, Shah, and age is given. Two numeric values are there, 35 and 32. Now here subject determines the faculty and faculty determines the age. Then we can say that subject determining faculty and faculty determining age. That is, this is determining A is determining B and B is determining C. Then we can say that subject determines the age. That is the example of transitive functional dependency that we need to look. Now, while studying these functional dependencies, that in second normal form we need to remove the partial functional dependencies. And how can we remove the partial functional dependency? So that first we need to know what is partial functional dependency, only then we will be able to remove it. Then in third normal form we need to remove the transitive functional dependency. So how can we remove the transitive functional dependency? That is only first finding it out what is transitive dependency, only then we will be able to eliminate it in third normal form. So therefore, as per the rule of transitive dependency, subject determine age holds. It makes sense, because if you don't know the subject name, we can know the age of faculty. Now there is another classification, that is trivial FD versus non-trivial FD. So what is trivial FD? X determine Y is a trivial FD if Y is a subset of X. For example, roll number, department name and semester determines roll number. So here we see that roll number itself is a subset of X, that is roll number is a subset of X, which means this is an example of a trivial functional dependency. Non-trivial functional dependency, X determine Y is non-trivial if Y is not a subset of X. Let us see. Roll number, department name and semester determines the student name. This student name is not the subset of determinant part. As we are saying, none of the attributes contain the student name, therefore it is the non-trivial FD. Now let us see some rules related to functional dependencies, and these rules are known as inference rule. So we will be studying them one by one. In totality, there are 6 inference rules. Out of them, 3 are axioms, Armstrong axioms, also known as rat axioms, and 3 are different rules. So in totality, we are having 6 rules for functional dependencies, and those are known as inference rules. So first we will be studying reflexivity. That is, reflexivity means that if B is a subset of A, then we can say that A determines B. Second is augmentation rule. As we are seeing, if A determines B, then we can say that A determines BC. Third is transitive rule. That is, if A determines B and B determines C, then A determines C. That is transitive rule. Third, now all these 3 rules, first 3 rules are known as rat axioms. Rat axioms, that is, these rules do not have any proof. We assume that these are true. Such a statement is known as axioms. Now next is pseudo transitive rule. If A determines B and B determines C, then we can say that AD determines C. That is pseudo transitive rule. Decomposition rules. If A determines BC, then A determines B and A determines C. Third, A determines B and A determines C, then we can say that A determines BC, that is union rule. So in totality, there are 3 axioms and 3 additional rules: pseudo transitive rule, decomposition rules and union rules. Now easily we can prove the rule number union rule, decomposition rule and pseudo transitive rule can be proved with the help of these axioms, rat axioms. Next we will be studying closure of set of FDs. That is, given a set of FDs, there are certain another FDs that are logically implied by F. That is, if A determines B and B determines C, then we can infer that A determines C. This is by transitive rule. So closure of set of FDs that is logically implied by F is called closure of FDs. Means from given FDs, which new FDs we can derive using the current FDs as well as the inference rules. We shall be using the inference rules to derive new FDs from the current FDs, that will be the closure of set of attributes. That is denoted by F plus, that is indicated here. How to write? This is the F plus. Let us demonstrate it with the help of an example. Suppose we are given a relation schema R having the attribute A, B, C, G, H, I and set of FDs are A determines B, A determines C, CG determines H and CG determines I and B determines H. Now from these FDs we have to derive new FDs. So how we can try new FDs? Using the inference rules. First, A determines B and this A is determining B and this B is determining H. That is this one. So A determines B and B determines H. Now using the transitive rule, we can say that A determines H. That is one. Clear cut? By transitive rule, we can say that A determine H. This is how we are driving the FDs. Now let us see next FD that we can drive is CG determines H and CG determine I. That is, now we will be applying union rule on that. This, by applying union rule, what we will be getting? CG determines HI, we will be getting CG determine HI. Now A determines C and CG determine A determines C and CG determine I. Now applying the pseudo transitive rule. Now this will give AG determine I. This is by applying the pseudo transitive rule. Now again we are seeing A determines C. Now we are applying the augmentation rule, that is AG determine CG and CG determine I. This means AG determine I. Again we are getting this FD. So in a nutshell, we are seeing that we can drive a lot of FDs with the help of given FDs, and that will be known as the closure or F plus. Now see the next question. We are given a relation R having the attributes A, B, C, G, H, I and set of FDs are given. Now we need to find the closure. So what will the closure? What will the set of F plus, that is closure of set of FDs? A determines H by applying, first is A determines H by applying transitive rule. Now CG determine HI, this we are getting, and AG determining AI. That is, already we have already completed these. We have already computed all these as I was discussing. So this is the F plus. Now let us see a different question whereby we have a set of attribute A, B, C, D, E, F and a set of FDs. A determines B, A determines C, CD determines E and CD determines F and B determines E. Now we have to calculate the closure of set of FDs, that is F plus. Let us see how to compute it step by step as we have done in previous steps. We need to use the inference rules to drive to extract new FDs. Let us see how. First A determines B and A determines C. If we apply the union rule, we can say that A determines BC. First FD that we have derived. Now second, CD determines E and CD determines F. Then we can say that CD determines EF. Second rule, that is second FD we have computed. Now third, A determine B and B determine E. Now that is, we will be applying the transitive rule, that is A will determine E. Now A determines C and CD determine E. Now this is the pseudo transitive rule. A is determining C and CD is determining E. Then we can say that A, then the common attribute here is C. AC determine, AD determine E. That is the pseudo transitive rule. By applying, we get AD determine E. Now A determines C and CD determine F. Then again we can say AD determines the F. These are the set of FDs that we have computed. Now, so what is the answer? The answer will be all these FDs. A determine BC, CD determine E, A determine E, AD determine E, and AD determine F. That we will be getting the answer the following questions. Now one more question we can see is, we have to compute the closure. Again there are 5 attributes A, B, C, D, E, and A, B determine C, D determine AC, and D determine E. Now we need to find the closure of F. Now A, D determines A, C. This means we can apply the decomposition rule, and by applying the decomposition rule we will getting D determine A and D determine C. Next, D determine AC and D determine E. Now if we apply the union rule, we will be getting that D determine A, C, E. So the answer will be D determine A, D determine C, and D determine A, C, E. Now next is closure of attribute set. Let us see. Closure of set of attribute means that given a set of attribute, the closure of that particular attribute alpha under F is the set of attribute that is firstly determined by the F. That is, if we compute the closure of a particular attribute, it means all the other attributes that are dependent on it. So why do we compute the closure of set of attribute? In order to find out the set of attributes that are dependent on alpha, means that we need to find out which attribute determine all other attributes. That is, to compute the candidate key of a relation, we need to find out the closure of set of attribute, which can be easily computed with help of a simple example. Now, in order to compute the closure of set of attribute, we need to apply the algorithm to compute alpha plus. Now the steps are: initially result equal to alpha, while changes to result do for each beta in gamma do begin. If beta is subset of result, then the new result will be result union gamma, else result equal to result, and thereby the end. Now let us see how to apply this algorithm to compute the closure of set of attribute. Consider the following relation R having the attribute A, B, C, G, H, I. For this relation, a set of FDs are given. A determines B, A determines C, CG determines H, CG determines I, and B determines H. Now we need to find the closure of AG plus. So initially, how to find it out? Step number 1, result equal to AG. Now next, first FD is A determines B. Now this A is a subset of AG. Then result equal to AG union B, that is ABJ. Next FD is A determines C. Now this A is a subset of ABJ, that is result equal to ABJ union C. Result will be ABCG. Next CG determine H, that is this CG is a subset of the result. Therefore, in new result we will be including H. Now the result will be ABCGH. Now CG determines I. Now this CG is a subset of the result ABCGH. Therefore, the new result will be ABCGH union I, that is result equal to ABCGHI. Now AG, the closure of AG consists of all the attributes. Closure of this consists of all the attributes. So we can say that AG is the candidate key for the relation, since it consists of all the attributes. In addition to that also we can find out the closure of set of FDs. So this topic will help us to find out the candidate key or the super key for a relation. For that we can use the algorithm line by line and find out which attributes determines which particular attributes. If a attribute or a combination of attribute determine other attributes, we can say that all other attributes, then we can say that it is a candidate key. If it does not determine all the attributes, then it is not a candidate key. It may be determinant for some of the attributes but not for the whole. Only candidate key or super key is determinant for all the attributes of the relation. I hope it will make you clear your understanding of functional dependencies. Thank you.